Hello, welcome back. We have been talking about Maxwell's equations, and we saw that Maxwell's equations are a synthesis of all electromagnetic phenomena. And now we're going to see how those equations can be applied to electromagnetic waves. Maxwell was the first to understand that light is an oscillation of the electromagnetic field. Maxwell was able to predict that electromagnetic waves can exist at any frequency, not just the frequencies of visible light. What that means is that we have a full spectrum known as the electromagnetic spectrum. Here is an image of the electromagnetic spectrum, ranging from the long wavelength radio waves all the way up to the very short, but shorter wavelength X-rays, and even shorter wavelength gamma rays. So at the time, radio waves hadn't been discovered. So this prediction was the harbinger of radio waves. So let's review Maxwell's equations and see how we can use Maxwell's equations to come up with electromagnetic radiation. Maxwell's equations lead to a wave equation for the electric and magnetic fields. So let's start by remembering what the Maxwell's equations are. The first is just Gauss's law, and we see that is the integral of E dot dA equals Qn over epsilon naught. Then we saw Gauss's law for magnetism, which is the integral of B dot dA, and that's equal to 0. Faraday's law tells us that the integral of E dot ds is equal to negative d phi sub m dt. And the Ampere Maxwell law, which tells us that the integral of B dot ds equals mu naught I through plus epsilon naught mu naught d phi sub e dt. So now what we want to think about is if we have an electromagnetic wave, and we're talking about light isn't charged particles at all. So there are no charges and there are no currents. So let's get rid of all charges and currents here. So Q in, nope, that's gone. So this will just be 0. And here we have I through. That current will also be 0. So rewriting Maxwell's equations with no charges and no currents, we see that we have Gauss's law that's set equal to 0. Gauss's law for magnetism is also still equal to 0. And we see that now, and the Ampere Maxwell law just has the additional term that Maxwell added, epsilon naught mu naught d phi sub e dt. So let's think about what this means, what these laws imply that give us electromagnetic radiation. So the first idea is that a changing magnetic field creates an induced electric field. So if a changing magnetic field creates an induced electric field, and then we also have the fact that a changing electric field creates an induced magnetic field. So we can go from a changing electric field to an induced magnetic field. And then if that's changing in just the right way, we can get back to an induced electric field. And so if a changing magnetic field creates an electric field, that in turn happens to change in just the right way to recreate the original magnetic field, then the fields can exist in a self-sustaining mode. So using that, based on that assumption, now we want to see how this would work. Well, if our electromagnetic waves are self-sustaining, then the idea would be that they are planar waves. So if they're planar waves, what does that mean? So the figure here shows fields due to a plane wave traveling along the x-axis. So they are moving along the x-axis. What we see is that when we look at these waves, we see that the electric field is equal everywhere in this direction, and the magnetic field is equal everywhere in this direction. And so the fields are the same everywhere in the YZ plane, perpendicular to X. Now we can also take a cross section along the X-axis and see what happens in that case. So here's a cross section along the X-axis of a planar wave that is moving, that is traveling in the X direction. And we see that in this case, So this figure shows that the fields at one instant of time do in fact change along the x-axis. So if we were to see what that would look like, we would see that we're getting some sort of change along the x-axis. And we see that these waves move with a velocity, v for the v of the electromagnetic wave, v sub em. So these changing fields are the disturbance that is moving down the x-axis at a speed of v sub em. So E and B of a plane wave are functions of the two variables x and t. It's moving along x, and it's varying with the velocity v sub m, which we know is dx dt. So it's changing in time, and it's changing in x in one dimension. We're just looking at these in one dimension. So if these are planar waves that vary in one dimension, let's see if that works with all of our Maxwell laws. So first, we're going to look at Gauss's law, number one. So consider an imaginary box, a Gaussian surface or box, centered on the x-axis. So let's first look at the net electric flux through the box here when we're just looking at the electric flux. Now, we would, of course, also have the magnetic flux for this box in the same area, but we're trying to be simple. We're trying to simplify it and look first at just what's happening with the electric field. And we see that that the electric field that's coming in is the same electric field that's going out of our box. So there is no net flux through the electric field. And for the magnetic field, we see that the magnetic field coming into our box, all of the vectors that come into the box are the same that are coming out of the box. And so yet again, there is no net flux. The net flux through the box here is 0 for the magnetic flux. So is this what we would expect? Well, there is no charge inside the box because light doesn't have a charge. And for a plane wave, the net electric flux, net electric and magnetic flux through the box is 0. So the plane wave is in fact consistent with the first of Maxwell's equations. So that which told us that the integral of E dot dA when there is no charge inside the box will be equal to 0, which it is right here. And the integral of B dot dA should be equal to 0 as well. Now let's look at the next of Maxwell's equations. Look at Faraday's law. So in order to figure out Faraday's law, we're going to apply Faraday's law to this narrow rectangle here that's in the XY plane as shown. This is our narrow rectangle that we're looking at, and it's in the X-ray plane. And so Faraday's law, of course, tells us that the integral of E dot ds is equal to negative d phi sub m dt. So it's the integral. We're going to integrate around this box, and that should give us the change in the magnetic flux. So let's first try to figure out what's going on the right side of our equation. Let's try to figure out what is going on with the magnetic flux. So the magnetic field B is perpendicular. It's perpendicular to the area, to the rectangle. And so when we take our flux, we know that our magnetic flux is going to be equal to the magnetic field dotted with the area. And so in this case, the magnetic field dotted with the area will be BZ, a rectangle, which will just be BZ H, that's the area, that's the height, times delta X. So H times delta X, that will be the area. So we can just say that the flux is BZ H delta X. Now, as the wave moves, the flux will change at the rate. I'm going to take the derivative of this. And so that's going to be the derivative with respect to time of BZ H delta X, where H delta X is not changing. So we can pull that out, and we have the partial derivative of b sub z with respect to time. Now, b sub z is also changing in x, so that's why we have to do the partial derivative with respect to time to be specific that we're only interested in how it's changing in time. So that gives us this part right here. This gives us what's happening on the right side of Faraday's law. Now let's see what we can do for that integral. So now, looking at our box, we see that the electric field points in the y direction. The electric field points in the y direction. So at all points on the top and bottom edges of the integral, these points here will all contribute 0 to the integral. So nothing will be so nothing on the edges of our rectangle will count into our integration. So the only part of the integration that we're interested in is e of x over on this side, and this will be e of x plus delta x. So along the left edge of the loop, at position x, e sub y has the same value at every point. So e sub y along the left edge right here has the same value at every point. So now Faraday's law, which we have already seen, is the integral of E dot ds, which is equal to negative d phi sub m dt. So that's going to become, we'll look at the integral of E dot ds is going to be equal to d E sub y dx. So that's what this is here. This is E sub x, and then we're going to E sub x plus delta x. So that's going to be d E sub y dx, how E sub y is changing in x. And again, it's a partial because E sub y is also changing in time. And that will multiply by the area, so h delta x. And that, of course, will still be equal to negative d phi sub m dt. So now we remember that we had found before, we just found on the last page, that d phi sub m dt is equal to db sub z dt times h delta x. So I can put this in right here. And so I can rewrite this as dE sub y dx h delta x equals negative dB sub z dt h delta x. Dividing through by h delta x, the area of the rectangle itself cancels. So it doesn't matter how big our rectangle was that we chose. And what we're left with is dE sub y dx equals dB sub z dt. And those are partials again. So that's what Faraday's law gives us. Now let's look at our last equation. We're going to look at the Ampere-Maxwell law. So in this case, we're going to use a rectangle that is now in this case in the xz plane. So it's in the xz plane. And in this case, we'll apply the Ampere-Maxwell law, because now we're interested in the integral of b dot ds. So that's why we want to go in the xz plane in this case. So we remember that the Ampere-Maxwell law, when there is no current, is going to be equal to epsilon naught mu naught. Is the integral of b dot ds will be equal to epsilon naught mu naught d phi sub b dt. So it's the change in the electric flux with time. So let's try to start by looking at what is the change in the electric flux with time. So the electric field, as we see right here, is always perpendicular to the rectangle. And so the electric flux, which we know is E dot A, will be E in the y direction here. So it'll be E sub y times the area of the rectangle, which will be the area of the rectangle here is just L times delta x. So it will be equal to E sub y L delta x. So now, as the wave moves, the flux changes, right? So we have to take the time derivative here again. And so when we take the time derivative of the flux, we see that that gives us again, it'll be d dt of e sub y L delta x, which will of course then be just the partial of e sub y with respect to time, L delta x. So that gives us this piece right here. So we've got this, the right-hand side of our equation right there. Now let's see, we want to integrate around the triangle to get the Ampere-Maxwell law. And so if we're integrating around the rectangle rather, the Ampere-Maxwell law, in that case, we're going to integrate around the rectangle here. And we again see that on the edges here, that's just going to be equal to 0 because there is when we're integrating b dot ds, there is no b in that area. So b dot ds would be 0. Now b dot ds for the other, for the leftmost side, those are all, everything along this side of the rectangle is just b sub x. I'm sorry, b sub z, we're in the z direction here. So it's just b sub z. And so we see that we have b sub z of x, and this is b sub z of x plus delta x on this side. So when we integrate, we're going to have the the partial derivative of b sub z with respect to x times the area of the rectangle, which is L times delta x. And that will be equal to the right side of our equation, epsilon naught mu naught d phi sub v dt. So we've got, which we remember from what we found before, that d phi sub v dt is equal to dE sub y dt of L times L delta x. So putting this in right here, we can then say that this gives us negative d diva dx of b sub z L delta x equals epsilon naught mu naught diva dt of e sub y. And so we can then the L delta x was still there with L delta x right here. And so now the L delta x cancels on both sides. The area of the rectangle cancels. And what we're left with in this case is dBz dx equals negative epsilon naught mu naught d e sub y dt. So if we start with the Faraday's law requirement for any electromagnetic wave, we can take the second derivative with respect to x and combine this with the Ampere-Maxwell law to then obtain the wave equation. So in that case, we would have d2 e sub y dt squared equals 1 over epsilon naught mu naught d2 e sub y dx squared, which is the wave equation for electromagnetic waves. Now we remember that the general wave equation, in the general wave equation, this is the speed squared. And so since this is the form of the general wave equation, we see an electromagnetic wave must travel with a speed of 1 over the square root of epsilon naught mu naught, which we know is then 3 times 10 to the 8th meters per second, which is equal to c, the speed of light. So let's now look at bringing all of these pieces together to get the properties of an electromagnetic wave. So we see that an electromagnetic wave is in fact a planar wave, and that planar wave is a sinusoidal wave that has frequency f and wavelength lambda and travels with a speed of v sub em, which we know is equal to c, the speed of light. Now, we know that E and B are always perpendicular to each other and also to the direction of travel. The fields have amplitudes E naught and B naught. And we also see that E and B are in phase. So when E is a maximum, B is at a maximum, and they both have zeros at the same point, and their troughs are also at the same point. The field strengths of the electric field and the magnetic field are always related by E equals C times B at every point on the wave. So Maxwell was able to use the equations that he had summarized together and made a synopsis of all of the electromagnetic equations that had been seen so far, and was able to deduce that light itself is an electromagnetic wave. And not only was light an electromagnetic wave, but that there was a full electromagnetic spectrum ranging in all different frequencies that traveled as electromagnetic waves.